Well, hi there. Thanks so much for showing up for your learning. It's Mr. Jennings. And today we are revisiting the unit circle, which, I don't know, if it's not your favorite thing, why not? It's like perfection. Okay, so let's take a look at how we're going to use it in grade 12. So the main thing is we're going to be updating our skills, just looking at developing our fluency with it a little bit more for like exact values from special triangles. That's very much a grade 11 topic. Using the cast rule is also just grade 11. And using related acute angles to solve problems, also 11. A lot of dittos here. Recognize it. It's just like, oh, there it is. Oh my goodness, I see the unit circle. And we're also going to see things in radian measure as opposed to degrees today. So let's dive in, shall we? It's going to be a longer one. That's why I brought myself an emotional support stuffy. Let's go. So you'll recall that this is the coordinate plane, generally known as the XY plane or the Cartesian plane. And this is the origin, and that's where our angles start. Okay, and we're going to draw a ray out from there somewhere. So we call the x-axis the initial arm. Because we kind of need two things in between to open up an angle, right? Like if I just do this with one finger, I just look like a weirdo. But if I do it with two fingers, I'm clearly just making an angle. Either that or it's a gang sign for the V gang or something, but that's weird. Let's not think about it too much. So here we go. There's my angle in standard position. That's the positive direction. This is the terminal arm. And then if I went like, I don't know, this direction, wee, and that would be the terminal arm still. Whereas this might be like a negative 135 degrees, or what is that? Negative 3/4 pi. Okay. This one would be like 1/4 pi, or pi on 4. That's a weird way to say 1/4 pi, pi on 4, or 45 degrees. Okay, in the positive direction. Okay, now we got angles, coordinate plane. All right, let's go. You draw them a different way, you're wrong. Okay, now cast rule. Cast rule is super easy because we spell it for some way this way, like C-A-S-T. It goes that way. And that always tells you which one of your primary trigonometric ratios, cosine, sine, or tangent, is positive in that quadrant. So if we are in quadrant A, which is angles from 0 degrees to 90 degrees, or 0 to 1/2 pi, then all of your ratios are positive. But once you go over here, only sine is positive, and cosine and tangent flip to negative over here. This is why you'll sometimes see negative values of cosine inside a cosine law triangle. And because we can still have angles like this in a triangle. You can have an obtuse triangle. Anyhow, sine is positive still over here, because you'll also recall that when you have an angle, let's just go to another bright color like orange. If I say have this angle out here, and I find that point on the unit circle, which we're going to talk about in a minute, okay, then this point would be given by the x value is cosine of theta, and the y value is sine of theta. Okay, so because the y value is still positive up there, then sine is positive in this quadrant. That's the way I remember it. And that's also why cosine down here, where if we have this point there, the x value is given by cosine of theta, and the y value is sine of theta. So cosine's positive over this way, and that's why cosine's positive down here. Tangent's positive over there because tangent's a ratio of x to y, and since both of them are negative over there, and both of them are positive over here, a ratio of a negative to a negative is a positive, so that's why that works out in that way. Okay. So, suppose we were given this problem without a calculator. My goodness, the arithmetic we're going to need to know. So, we're told that tan A is 4 on 5 and that it's in quadrant 1. So we're going to go ahead and draw our coordinate axes. We know that tangent is towa, opposite over adjacent, or in other words, the opposite side is the y value divided by the x value. The adjacent's always, the opposite is always y, and the adjacent is always x. Okay, so I'm going to go ahead and draw on our angle here. Our opposite is 4 and our adjacent is 5, so we're ever so slightly below 45 degrees. So we are some kind of line like that, where this could be, if you were to draw a triangle there, that would be like 4 and that 5. So this is the point 5,4. And now we might want to know our hypotenuse. From Pythagoras, you have a squared plus b squared equals c squared. And you should always write that out. The amount of times I see students trying to do this stuff in their head and making an error just makes you want to barf in a bucket. So I've defiled enough buckets in my day, so I'd appreciate it if you would write out your formulas in full. So then you go ahead and sub in. So then you got 4 squared plus 5 squared equals the hypotenuse squared. And 4 squared is 16, 15, 5 squared is 25, equals h squared. Call it h, not hypotenuse. And then 41 equals h squared, and plus or minus root 41 is equal to h. Why plus or minus, you say? Well, negative numbers square to positive numbers. So we always, whenever you use that inverse operation of square root both sides, please add a plus minus, or else an angel loses its wings, or maybe a bunny loses, a duck loses its ears. I don't know. So this is clearly positive. The hypotenuse is always positive, so this is root 41. All right, so now we want to find the exact value of cosine A. Okay, so cosine of A, this is angle A, okay, all right, cosine is always adjacent over hypotenuse. That's great, we just saw it for the hypotenuse, the adjacent, well, I don't want to write that out. Okay, so the adjacent is 5, and the hypotenuse is the square root of 41, so we're done, right? There it is, that's the grade 11 answer, right? No, we want to be able to rationalize denominators in this course. So what we're going to do is we're not going to circle that because it's not our final answer. And we're just going to multiply top and bottom by something that's going to make the denominator a rational number. Okay? This is kind of just for style points, but it's also, it's like what you just expected to have the skill. Okay? So mathematicians appreciate it. So we have 5 root 41 over, what's root 41 times root 41? 41. Okay, so 5 root 41 on 41 is our final answer. Yay. Let's keep going. All right, so do this one without a calculator. Pause me and then check back in with us, okay? You back? Great. Let's go. So draw your diagram. We're told that we have angle A in quadrant 4, so we're going to draw our x-axis and our y-axis, and we're going to put it somewhere on quadrant 4, okay? Because these are 1, 2, 3, 4. Just to review. And tangent is indeed negative in this quadrant, so that shouldn't surprise us. We're going to draw that on, put a little point on the end, sure, why not, and then call this angle A. All right, and then we know that tangent is equal to opposite over adjacent, which is a fancy way of saying the y value over the x value. Yeah, so we know that this here side is minus 5, because that makes sense just because it's down there, and that this side over here which makes a right angle, of course, is the square root of 119. And now we want to know sine A. Okay, well, I suppose we should find out h, the hypotenuse. So we have from Pythagoras, a squared plus b squared equals c squared. And we just sub in minus 5, put it in brackets for the love of all that is mathematical, plus the square root of 119 squared, you could put that in brackets, but it doesn't matter, equals c squared. Minus 5 squared is the same as minus 5 and minus 1. 25 positive plus 119 equals c squared. 25 plus 119 happens to be my favorite number. 144. That equals c squared. So that means plus or minus 12 is equal to c, because 144 is a perfect square, just like me. So now, is it positive or negative? Well, h is always positive, the hypotenuse. It's a distance, so we always just use a positive value. Great. All right, so now we want to find the exact value of sine A. Okay, so sine of A is the opposite over the hypotenuse, which in this case the opposite is minus 5 and the hypotenuse is 12. And you know what? That is simplest radical form. We're using a rational denominator. Can't get simpler than that. It's a rational denominator. 12 is a rational number. So what else to say about that? Well, you have cast C-A-S-T. Sine is positive over here and here where they're all positive. So sine is negative down here where only cosine is positive. And indeed, we got a negative answer. So that is a way of error checking using cast rule. Let's keep going. Recall these? I hope so. We're going to be talking about them. Yeah, they keep coming up. We keep being interested in them for one reason or another, but they're kind of outdated. Sine, when you flip it, is cosecant. Cosine, when you flip it, is secant. And then tan, when you flip it, is cotan. All right? Here's something that if you don't know, may help you remember these. Secant and sine kind of go together, except there's always one co in each pair. Cosine already has its co, so it just takes secant as its dance partner. Sine doesn't have a co, so cosecant has a co in it. And tan, its friend is cotan, and cotan has a co. Because that's how I remember which ones go with which. You can do it however you want. Maybe get a tattoo. All right. So now let's see if without a calculator we can do this. Okay, we're told cosecant A is root 29 on 2 and that it's in quadrant 2. Oh, it is, you say. Well, I happen to know cosecant A, that already has a co in it, so that's equal to 1 over sine A, which would be equal to hypotenuse over opposite. Okay, it's just the flipped version of sine. And no wonder it could be in quadrant 2 because cast, right? And CAS, cosine, is indeed positive in quadrant 2. So that's why that works in that way. All right, so let's go ahead and draw some general angle that hits in there. I guess the opposite is pretty small, so I could go a little further because it's only 2 over root 29. And root 29 is about 5.5 or so. So we're going to put our angle like pretty darn close to down here. Okay, so let's put it like that. And then here's the things we know. Okay, we know that this is root 29 because that's the hypotenuse. And that this is, the height of that is 2. All right, and then what's this? Oh, we don't know yet. Call that A for adjacent. Okay, and we're going to need the adjacent to find cosine of A in the simplest radical form. So how are we going to do that? We're going to say a squared plus b squared equals c squared. See how I write it out every time and I make fewer errors than y'all tend to? Well, I suppose that's not true. I make a lot of errors, but I also catch them. Okay, so A is a squared. Okay, b is 2 squared, and the hypotenuse is the square root of 29, which we're going to square. And so then you end up with a squared plus 4 is equal to 29. And would you look at that? Subtract 4 from both sides, everyone. Got to give it to us. A squared is 25. We got it. And that means A is 5. No, plus or minus 5. Okay? Because you always, when you do this, take the square root of both sides. You always add a plus or minus. You really only need to add the plus or minus to one side. Ask me why later, and I'll give you the simple answer. Okay, so if this is plus or minus 5, just looking at it, you can tell A is indeed negative 5 because it's negative in that direction. Okay, so this point here is given by negative 5, 2. That's that point that we're finding there. And so now let's find a cosine of A. It's already going to be pretty simple. Cosine of A. Oh, I bet it's going to be negative. Is equal to, well, it's the adjacent over the hypotenuse. And so that is minus 5 over root 29. And we certainly don't want to write it that way. So we are going to multiply top and bottom by the square root of 29. And then we wind up with this absolute, just such a handsome number, minus 5 root 29 over 29. Ugh. Okay, let's see if we can estimate its value and get pretty close. And so you can have fun with stuff like this if you want to be like me and find math fun. You can estimate its value and check on a calculator. It's like better than Geometry Dash, everybody, and way more mathematical. There's way more to do with math than the ostensibly named Geometry Dash. So I think that this is likely to be minus 0.89. Okay, 5, but it's negative times 29, but I take its square root, divide by 29 equals, I was too timid. I thought it was a little closer than that. Okay, anyway, so I thought it was negative 0.89. It's not 0.9293, more like, oof, I was out by 0.04. Okay, let's keep going. Oh, you remember these? These are the greatest. This is like the whole reason why we have like the no calculator stuff going on. Okay, this one is horribly drawn. Blah, it's a terrible diagram. Okay, if you take a square, like a proper square, okay, you'll note that a square has a right angle and these sides the same. Turn it into an isosceles triangle this way, and you'll note that this is 45 degrees, or in other words, pi on 4. This is also 45 degrees because isosceles triangles have two the same angles beside their legs. And if this were length 1 and this were length 1, we would have 1 squared plus 1 squared equals h squared, the hypotenuse. And that means the square root of 2 is h. You're allowed to forget this stuff if you can build it back again. I can do both. I have it memorized and I can build it. So you want to be like that. Okay. This one is a little funnier, but this will be the second time I've talked about this today. So if you take the 30, 60, 90 triangle, okay, drawn beautifully like that, here's the 30 degrees, here's the 60 degrees, here's the 90 degrees, and then you just hold up a mirror to it. Nice orange and blue mirror, okay? And you just mirror it down there. 90 plus 90 makes 180. That means that's a straight line, folks. Okay? And guess what? We just made, that's 60 degrees and that's 30 degrees. What do you know about triangles that have 3 angles the same? They're called equilateral triangles. Okay? So that is to say, if that were edge length 2 and that were edge length 2, this would be 2 and, well, sorry, no, that's just like 1 there because I'm going to do it as 1 plus 1, right? That's 1. and that's 1. Okay, so this is how you can remember that this side is 1 and that side is 2 and this side is the square root of 3 because of these types of reasons, right? 1 squared plus something squared, call it b squared, equals 2 squared. 2 squared is 4, but I take away 1 because I want to take away this 1 from both sides. So that means b squared is 3, and so b is the square root of 3, and for convenience sake we're just going to consider the positive one. So that's where these numbers come from. I have a really long lesson and I'm teaching you stuff you probably already know. But if you didn't know that already, you really want to know that and the why, okay? Don't just memorize this stuff, understand this stuff, and it makes it far more interesting. I promise. Okay, so what is the sine of 30? Well, the sine of 30 is 1/2. Why? Because it's a ratio of 1 to 2, opposite to hypotenuse, okay? That's for the pi on 6 angle. For cosine, it's adjacent to hypotenuse, so it's root 3 on 2. And tangent is opposite over adjacent. So it's 1 over root 3. Done, right? Not on your life. You got to rationalize this denominator. So we're going to multiply by root 3 over root 3. So that will give us root 3 on 3. That's kind of new content, so you want to have this level, okay? You want to be able to rationalize denominators and write things in the nice form, or else Hopper gets angry. Okay, so let's carry on with this triangle. So pi on 4, okay, so we're in this triangle over here. Sine and cosine are the same. Opposite over hypotenuse happens to be the same thing as adjacent over hypotenuse. So that's always 1 on root 2 or 1 on root 2. Hold on now, you're probably saying, don't get Hopper angry. Make sure that it works out nice. So it's root 2 on root 2 that we're going to multiply by, and that gives us root 2 on 2. It is the same thing here and here. How about tangent? Well, it's opposite over adjacent, so that's just 1. Boring. Okay, then what about pi on 3? Well, let's just clean this triangle up, and rather than consider this is our angle of interest, we're going to make this our angle of interest, all right? That's pi on 3. That's 60 degrees. How do I know that's 60 degrees? Because pi is like basically the same thing as 180 degrees, okay? So if I do pi on 180 degrees multiplied by 60 degrees, of course I get pi on 3. Okay, that's our conversion. Just reviewing. Okay, so sine of this is opposite over adjacent, so we are root 3 on 2, and you probably noticed that it's just the flipped version of that. It's like the cosine becomes the sine and the sine becomes the cosine, in other words. Cosine is 1/2 from here because it's adjacent over a hypotenuse. And what can be said about tangent that hasn't already been said? Opposite over adjacent is just the square root of 3 on 1, so we're done there. Let's keep going. Okay. What about this though? Okay. So one thing that would really help here, cosecant is just equal to 1 on sine. So if I was asked for the cosecant, I'd just take that one and flip it. So it's 2. Okay, the secant is 1 on cosine. So it's 2 on root 3. Right? Oh, but wait. That would be equivalent to over 3. 2 root 3 on 3. Okay, so convert. Convert for Hopper's sake. And then cotangent is just flipped tangent. So instead of, we're not going to bother flipping that one. Just flip this one. Okay, because that one would already be rationalized. This is just root 3. These ones, I mean like 1 on root 2, but we flip it, right? Because, wait, yeah, we just flip it because cosecant is going to be hypotenuse over adjacent, so that's just root 2. Secant is the same, it's root 2. And cotan is also 1, because when you flip 1, it's 1. It's the cotan is this one over this one, if we're looking at that as our angle of interest. But of course it's the same. Okay, now this one. And you'll recall that we could just take the secant and make it the cosecant, right? 2 root 3 over 3. Why? This is our angle of interest. We have cosecant, and cosecant is hypotenuse over opposite. Okay, so in this one, hypotenuse over opposite is just 2 on root 3, but then we rationalize the denominator. Secant is just going to be 2, because it's hypotenuse over adjacent for secant, flipped cosine. And then cotan is root 3 on 3, okay, because we would get, we would do, for cotangent, sorry, we do adjacent over opposite, but 1 on root 3 is got an irrational denominator, and you know how Hopper feels about that. So we rationalize the denominator. Okay, next thing, let's try dividing up each of our following circles into the special angles. We're going to do the 90 degrees here, and those are the pi's on 2. Okay, we're going to do the 60 degrees here, and those are the pi's on 3. We're going to do the 45 degrees here. Those are the pi's on 4. And is there one for pi on 5? No, there isn't. Okay, that'd be 72 degrees. And when was the last time you saw 72 degrees in a problem? Not very recently. So we're going to do 30 degrees here. And those are the pi's on 6s. Okay, this is memorize this stuff. This is repeat and memorize. So do this yourself and then see how you do. Hi. So if I divide this up into 90s, basically I can take a pizza cutter and do that. And then a pizza cutter and do that. And then this is pi on 2. This is pi. This is 3 pi on 2 down here. And then this is 4 pi. Sorry, 4 pi on 2. 2 pi. Gosh. 2 pi or 0 at that corner. All right. Let's trade colors each time. So for the 60s, I'm just going to put the center on. 60s, I can kind of go through like a maniac with my pizza cutter this way and this way thereabouts, and then this way, dividing it up into, would you look at that? The 180 degrees, each split into 3 slices, just like this promised. This is pi on 3, that's 1/3 of 180. This is 2 pi on 3. 3 pi on 3 would just be pi. Okay. This is 4 pi on 3. This is 5 pi on 3. And this is 6 pi on 3 or 0. It's the same. 6 pi on 3. 2 pi. Oh my goodness. All right, let's get out a new pizza cutter. We're going to cut up this circle in a number of ways. All right, so there's our first 180. Here we can use the 90s here because 90 has a factor 45. And there we're finally like, this is like the 1 pizza, 8 people. This is like our golden pizza sharing opportunity here. All right, and so our first 1/4 pi is there, pi on 4. And then we go there, that's pi on 2. And then this would be 3 pi on 4. And then this is a 4 pi, which is weird because it's only half of the pizza. And then we go down here, and that's a 5 pi on 4. This is 6 pi on 4, but we have a better way of saying that, 3 pi on 2. And then this is 7 pi on 4, otherwise known as 315 degrees. I have someone's infiltrating. I think they're going to try and steal Hopper from me. But I still have a lot of lesson left to go, and I need this emotional support, Stuffy, to get through it. Would you be so cruel as to take Hopper away from me? No? Okay, good. That's very kind of you.
The only thing I need you to do is put me to bed.
Oh, yeah. Oh, I'm so sorry. It's so late. It's been a hectic day, honey. Okay, so let's do the 30 degrees, and then I'll pause this lesson and put my children to bed, because, you know, life and stuff. So, oh, that wasn't very 30 degrees, but we'll be fine. Oh, you're going to make an appearance too, are you? Oh, I see.
They all want bed.
They all want to go to bed. Okay, look at that. This is going to be a mess, eh? So this is the first 1/6 of 180 degrees. So that's pi on 6. This is, oh, we've seen that already. That's pi on 3. Yeah, you can take them in a second. This one we've seen already. That's pi on 2. And this one we've also seen already. That's 2 pi on 3. But then here, well, that's 5 pi on 6. How did I know that so quickly? Even though my children are distracting me, I can count. 1, 2, 3, 4, 5. Okay, how many degrees is that? Well, it's 150. Okay. And then down here, that's pi. 7 pi on 6. This one we've seen already. It's 8 pi on 6 or 4 on 3 pi. And this one is 3 pi on 2. What are you doing over there? Pulling out leaves? Oh, you're pruning a plant. Great. That wouldn't. No one could find that distracting. No, that's impossible to be distracted by that. Okay, and then this one is going to be, gosh, what is it? 11 pi on 6. How did I do that? Well, it's 1/6 less than 2 pi. Okay, so those are those ideas, everybody. I'm sure Hopper is very pleased with that. Hopper may need to join some children for their bedtime, but I will continue this in just a moment. Oh, geez, half an hour already. All right, so fractions of pi. So we've talked about the unit circle for a little while so far, but really the main thing about the unit circle is we have a radius of 1, and that makes it the unit circle. Okay. The cool thing about that is if I give you this point and this angle, you can find the location of that point. Its coordinates are cosine of theta is the x value, and sine of theta is the y value. Okay. And why does that make sense? Well, here's the x component of that point, and there's the y component, and of course that's the opposite, and that's the adjacent. So cosine of that angle would be equal to the x value over the hypotenuse, which is 1, and the sine of that angle would be equal to the y value of that point over 1. Okay, because that's like the x component and that's the y component. Amazing. Okay, and there's a unit circle all filled in. Some people like to print these out. It's not the kind of beautiful thing that I'd want to like mount on my wall or have like an artistic impression of. So I prefer just to know how to build it myself rather than printing it out and looking at it. So this is all terminology that we want to like be really clear on so that you can use the proper terminology. Nothing says a noob like having to describe stuff that like people have agreed on a name about. The initial arm is the x-axis, right? It's that ray, which would be the x-axis. And then the terminal arm is the ray that's at the end of the angle, okay? And then the angle that's between it there, we call that the principal angle. And the related acute angle is the angle, the acute angle, there's always going to be one, unless we're talking 90 degrees or 270 degrees. Okay, there's always going to be an acute angle between the terminal arm and the x-axis. That's the related acute angle. Okay, so those are useful things, right? The mistake students will make is they'll start making angles from the y-axis, and that's just nonsense, so don't do that. Okay, angles are always from the x-axis. Related angles or principal angles are always from the x-axis. And that will avoid a lot of errors. Okay, you see the related acute angle over here. Well, what's the purpose of related acute angles? Well, suppose this related acute, let's say this principal angle was 150 degrees, okay? And then, so that would make the related acute angle. Well, how would we find that? My goodness. You would take 180 degrees, boop, 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 and take away some amount. This would be the related acute angle R, call that r, okay, to get to 150 degrees. Well, that would be 30 degrees equals r, or in our new parlance, pi on 6. All right, so that's the related acute angle. Now you'll notice that like sine 30 degrees equals 1/2, and sine of 150 degrees is, oh gee, I forget, what is that? What is sine of 150? I'm gonna check on my calculator, 150, but I take the sine of it. It's also 1/2. It's the same. Why is that? Well, because if I went back over here and found that one over there, that would be the angle there, right? Like the y value of that point is the same as the y value of that point. So they're related, okay? And cosine similarly has a similar relationship there, but this one and that one would be opposite sines of one another. So cosine of 30 degrees, let's say, would be root 3 on 2, and cosine of 150 degrees would be root 3 on 2, but it's negative. So that's how these related acute angles are very useful. All right, let's keep going. So, in quadrant 1, the principal angle related, yeah, so in quadrant 1, it's the same. Yeah, like if I have an angle over there, it's silly to talk about the related acute angle because the principal angle and the related acute angle are the same thing. But there, you see quadrant 2, you have that diagram, and we find them like 180 minus the principal angle, so in this case 150, that would give you 30 degrees. Or you could say pi minus, well, what's 150 again? Oh, it was 5 pi on 6, and that would give us pi on 6 as the related acute angle. In quadrant 3, we have to do 180 plus the related acute angle, gives us that. 180 plus the related acute angle will give us the thing in quadrant 3. So here, this angle is 210, right? So we have the principal angle 210. So 210 minus 180 would give us 30 degrees. That's our related acute angle, or in this case 180 degrees. That is to say, if we did this and then we wanted to arrive at the terminal arm, we need to add on the related acute angle. So 180 plus 30 degrees equals 210. Why is this lesson so long? Because I keep on pointing at the obvious, that's why. So here, the related acute angle is 30 degrees, but you might also say, is that negative? No, we just think of the related acute angles as always being positive. I guess. I've never heard someone say a related acute angle that's negative anyway. So in this case, we have to do like 360 minus the related acute angle to get the principal angle. Okay, when they're in quadrant 4, or the principal angle plus the related acute angle should equal 360, which is to say 360 minus the principal angle gives us the related angle. In this case, 360 minus 330 equals 30 degrees. Let's keep going. So yeah, maybe try that a link and see what it has to show you. All right. So we want the exact values of the 3 primary. We're going to draw a diagram. Okay, so we're going to draw our diagram. That is a little bit shy of 1 full pi, isn't it? So it's over there. That's 5 pi on 6. And we happen to have this related acute angle here, which would be pi on 6. Okay, and then we think about cast, C-A-S-T. So only sine is going to be positive here. So sine 5 pi on 6 will be equal to sine pi on 6, because that's our related acute angle. We don't need to type 5 pi on 6. Okay, and I happen to remember that that's 0.5 or 1/2. Okay, now, how did I know that? Well, because I have this triangle memorized. Pi on 6, pi on 3, right angle. This is 1, 2, root 3. Okay, so that's the triangle that I'm referring to in my brain of brains. Now, cosine of 5, you can tell it's late, eh? I can't even write legibly. And now you might be saying to yourself, Mr. Jennings, you can't write legibly. Doesn't matter the time. In which case I say, I'm so sorry. That's equal to negative cosine of pi on 6. Why do I know it's negative? Because only sine is negative, so the cosine is negative, okay? Sorry, only sine is positive. All right, so that would be equal to, well, adjacent over hypotenuse, but negative. So root 3 on 2. Don't ask me that as is 0.866, but negative. Okay, and then tan of 5 pi on 6 is equal to negative tan of pi on 6. We just use a related acute angle, and that's equal to opposite over adjacent, which is, but it's negative, negative root 3 on 3, because I happen to remember that I need to rationalize my denominator. Just to review, 1 on root 3 times root 3 on root 3 is what I just said. How about 5 pi on 4? How about we do that? Okay, draw a diagram. Pi on 4, 2 pi on 4, 3 pi on 4, 4 pi on 4, 5 pi on 4. There it is. 5 pi on 4. Okay, so the related acute angle is here, pi on 4. Because I just have to do 180 plus 45 to get there. Pi plus 1/4 pi to get there. So that's how I know the related acute angle. Castrol, CAST, only tangent will be positive here. So sine 5 pi on 4 will be equal to negative sine pi on 4, which will be equal to negative 1 on root 2, but that's the grade 11 version, so this is root 2 on 2, but negative. Cosine of that whole same thing, it's the same, okay? Cosine equals sine down here. Okay. Yeah, it's the same. It's just different here and here when the signs are opposite, but the value is the same. And then tan, let's do tan. Tan 5 pi on 4 is equal to tan pi on 4, because it's positive over there, so it's just equal to what the reference angle is, the related acute angle. And that is, well, let's draw our triangle. I never did draw a triangle for this one, did I? Okay, so this one is 1, 1, and root 2, and tan is that one over that one, so it's just 1. Let's keep going. There's 7 pi on 2. This is a coterminal angle. That is to say, it's the type of thing that a math teacher cooks up to keep me busy for another 90 seconds. All right, so I better just get to it, right? So draw your diagram. Don't despair. 2 pi, or a fancy way of saying 4 pi on 2, 5 pi on 2, 6 pi on 2, 7 pi on 2. Imagine landing that ski jump. You jump up and you do a perfect, not quite 720. The wipeout would be fabulous. Okay, all right. So we land with our skis 90 degrees to the direction we're going. Whee! Okay, let's go. So now we know that that is the same thing as 270. So our reference angle here is pi on 2. Okay, it's 90 degrees. All right, that's our reference angle. So we have cast C, A, S, T, and it's hard to tell which one we're in. All right, so we're gonna take a look at that and just be careful. The X is 0 and the Y is -1. So we are going to say sine of 7 pi on 2 is equal to, well, negative sine, because the y's are negative, of pi on 2, which is equal to -1. Sine of pi on 2 is 1. Sine 90, 1. It's 1. And you can remember that from your function, right? There's the full 360 and there's 90 at the maximum, 1. Okay, there is this angle. Okay, what's the y value? 1. What's the hypotenuse? 1. So that's 1. Okay, so in this case, -1. All right, next cosine of 7 pi on 2. Well, it doesn't matter if we call it plus or minus. It's just cosine of pi on 2. It's at that point where it's neither positive nor negative because it's exactly 0. All right, and then tan. Tan of 7 pi on 2 is equal to, well, what's the tan of -270? It's equal to undefined. Okay, so 270, but I take its tangent, undefined. Why? You tell me. No, I'll tell you. Tan is equal to opposite over adjacent. Or you may remember like, oh, I came back from a tan and came back from vacation and I got a sine over cos. Right? The cos is 0. So this is actually a like tangent goes off to an asymptote there. Yeah, so because we have a 0 in the denominator, so it's undefined. Okay, so it doesn't matter if it's positive or negative. All right, okay, so let's do negative pi on 3. This is a negative angle. Yeah, so we're going to draw a diagram, and we're going to go down here. That's there, and that's negative pi on 3. And what are those? So cast C-A-S-T only cosine. So our related acute angle. Our related angle is just pi on 3. Okay, that's our related acute angle. So we have sine negative pi on 3 is equal to negative sine pi on 3, which is to say negative root 3 on 2. Cosine of negative pi on 3 is equal to cosine pi on 3 because, hey, cosine is positive, and that's equal to 1/2. And tan negative pi on 3 is equal to negative tan of pi on 3. Why am I whispering? And that's equal to pi on 3. Oh gosh. Just remember this stuff, right? You just want to be like, okay, opposite over adjacent is root 3. Negative root 3. There's so many examples. It's not that they're hard. Okay. Negative 1/4 pi. Negative 1/2 pi. Negative 3/4 pi. There it is. Here's my related acute angle, which is pi on 4. C-A-S-T. Okay, only tangent. Pi on 4 is equal to root 2 on 2, but it's negative. Cosine is same. The same, and tan is positive, so negative root 3 pi on 4 is equal to tan pi on 4 is equal, sorry, I'm making a weird noise, 1. Okay, so there's our 2 answers. Draw a diagram. I looked at this presentation before I went. I was like, yep, this looks good. This looks like about a half an hour. It's way more than a half an hour. It's about there, isn't it? That's like pi on 6 is my related acute angle. Cast. Okay. But this one's positive. Oh, it did say reciprocal, didn't it? How long has it been saying that? No, just there. So I just missed the one. I was just thinking, like, these, there must be something different about these. Because why am I doing so many that are the same? So those are the primary ones. So that's the good news. The bad news is there's still more work to do. So cosecant of theta is equal to 1 on sine theta. So that is to say I can just do this, and cosecant 7 pi on 6 is equal to negative 2. Secant is flipped cosine, so secant 7 pi on 6 is equal to minus 2 root 3 on 3. Sorry for cramping that, but I just flipped that and then rationalized the denominator. And then this one, the great news is that cotan was already rationalized of 7 pi on 6 is just equal to root 3. And there's those. All right. No, I'm just gonna do. This is craziness. This is much nicer. So, okay, so this is a negative angle. So we're going to do one of them. I'm going to do this negative angle for the reciprocal one. And yeah, this one is fine. So, okay, so here, negative 3 pi on 4. There's a negative 1/4. There's a negative 1/2. There's negative 3/4. It's 225, but by another name, it's negative 135. If you were to convert to degrees. Okay, so anyway, our related acute angle is pi on 4. That's our related acute angle. All right, and cast, so this is t, it's only tangent down there, or cotan in this case, is positive. So we have cosecant of negative 3 pi on 4 is equal to negative cosecant of pi on 4 is equal to, well, pi on 4, so yeah, it's root 2, but negative secant of negative 3 pi on 4, because this is a 45-degree triangle and they're both negative, it's the same, it's negative root 2. And then cotan of negative 3 pi on 4 is equal to cotan of pi on 4, which is to say it's like 1 on tan of pi on 4 because they're reciprocals of one another. And pi on 4's tangent is 1, so the reciprocal of that is 1. I can feel myself burning brain cells for nothing. Okay, so here, let's do this, folks. Let's do it. So we want to do cosine this times cosine that plus sine this times sine that. All right, cosine, so just work it out. All right, so cosine 2 pi on 3. 2 pi on 3 is draw a quick diagram. Pi on 3, 2 pi on 3, so we're 120 there. Cosine is 1/2 but negative, so this is negative 1 on 2. Okay. Cosine 5 pi on 6, so the one I drew wasn't a very good diagram. Cosine 2 pi on 3 is more like that. Cosine 5 pi on 6 is 5 pi on 6 is over here, like that, where this is pi on 6. As a related acute angle, just the way you would do that is like you would say, well, I have pi, which is all the way over here, and I want to take away something to get to 5 pi on 6, so I just do pi minus 5 pi on 6 to find my related acute angle, and it's pi on 6. Okay, so cosine of pi on 6 is root 3 on 2, but it's negative. Okay. Now I want to add sine 2 pi on 3, and sine 2 pi on 3 is 2 pi on 3 we discussed is this one here, and sine of that is root 3 on 2. And then sine 5 pi on 6. 5 pi on 6 is this one, and that's 1/2. So now we just have to do it. Right? And then simplify. Don't go doing decimals. Stick with the fractions and the rational expressions that you're not used to. Okay, so we multiply here and we get root 3 on 4 plus root 3 on 4, and that's equal to root 3 on 2. Yay. Yay. Big yay. Sorry, was that too fast? That's 2 root 3 on 4, which is equal to root 3 on 2. Please tell me it's... Oh man. So many more. Okay, I'm just going to go a little faster. I've been saying that for a little while, haven't I? Okay. Okay, secant pi on 4. So, draw a diagram. Pi on 4 is over there. Okay, it's 45 degrees. Secant is, that's root 2, because it's the opposite of cosine for that. And then cosine of 2 pi on 3. We just talked about 2 pi on 3. 2 pi on 3 is up there. Okay, and that cosine is 1/2 but negative. So root 2 times negative 1 on 2. Okay, so that's the numerator. Tan pi on 6. Pi on 6 is over here. That's the same thing as 30 degrees. So tangent of that is 1 on root 3. Mr. Jennings, do you need to rationalize your denominator? Nah. Not until final answer time. Cosecant 3 pi on 4. Well, cosecant 3 pi on 4. Let's find out what that is. So, cosecant 3 pi on 4. There's 1 pi on 4, 2 pi on 4, 3 pi on 4. So we're there. And cosecant is just going to be, well, this is 1 root 2. So we're this on top of cosecant goes with sine, so we're 1 on that, so it's positive root 2. Okay. This all looks correct to me. And then we can just cancel. Or you can multiply in. Doesn't really much matter. I'll do it the simplest way. You figure out your numerator, which is going to be negative root 2 on 2. Okay, and then figure out your denominator, which is root 2 on root 3. And this is a situation that calls for keep, flip, change, or flip and multiply. So this is negative root 2 on 2 multiplied by root 3 on root 2. And then what I wanted to do at the beginning is just cancel those. So then we end up with negative root 3 on 2. We want to be able to simplify these types of things and get it right, get the exact value. That's the last one, right? No, there's 2 more. Is that one really going to teach us anything we don't know already? No, this one will be slightly more interesting. 5 pi on 4. So draw a diagram. There's pi. There's 5 pi on 4. The reference angle is pi on 4. And so the sine of that is negative. So we have sine squared 5 pi on 4 is the same thing as sine of pi on 4, but negative, but squared. Pi on 4 is 1 on root 2. So this is 1 on root 2, but it's negative. And we square it. And we got to take away cosine squared of 3 pi on 2. 3 pi on 2. 3 pi on 2 is all the way there. Halfway to 2 pi from 1 pi. So the cosine of that is 0. But don't forget to square it. these examples. Gosh. Oh, plus the tangent to 4 pi on 3. Okay. The tangent of 4 pi on 3. Draw a diagram. There's pi. There's 4 pi on 3. 1/3 the way to 360 from 180. Reference angle pi on 3. Tangent is indeed positive over here. So this is the same thing as plus tan. Tan 4 pi on 3 equals tan pi on 3. Hooray! So tan pi on 3, let's just figure that out. Oh, this is root 3, this is 1. So tan is this on this. So it's just plus root 3. Oof, wow. Okay, so that's what that equals. And then we go, this is equal to, well, 1 on root 2 squared is 1/2. Don't believe me? What's negative 1 times negative 1? In your experience, is that 1? Was root 2 times root 2? In your experience, is that 2? Yes. Okay, so we have 1/2 plus root 3. Okay, and that could be written as a single kind of fraction. That's like 1 plus 2 root 3 all over 2. Okay, just going to multiply this top and bottom by 2 on 2 if I want to like kind of put it together on one fraction. Yay, practice everyone. So I think that's about an hour. So I will definitely be recommending that you watch this at 1.5 speed. Work alongside me on your practice problems. Refer to this video as like a reference for how to do these types of problems. And have fun with it like I'm having fun with it. Okay, bye for now, everyone. Or don't have fun with it. I mean, it's not your job to enjoy school. It's just your privilege. Bye.